Okay.
Let's start. See, these are some important formulas you must know. This is the mass flow rate formula, where rho is density, A is area of cross section, and U is velocity.
Yeah.
Okay. The unit would be kg per second. Then thermodynamics. What is the formula? This is formula MHFG. Do you know the term HFG?
No.
Okay, this is latent heat.
Oh, latent. Okay.
Latent heat of evaporation. Okay. Do you understand the difference between sensible heat and latent heat?
No.
Okay. So whenever you supply heat to an object, okay, whenever you try to heat a substance or a material, there can be two possible change the body would or the object would show. One would be when you supply heat, the temperature would change.
Okay.
And another would be when you supply heat, the phase would change.
Okay.
Right? So how is it? The flow is like, initially if you have a solid, and if the solid is heated, then that heat would raise the temperature of that solid.
Yeah.
The solid becomes hot solid. Okay. Hot solid. And this process is called as sensible heating of solid.
Okay.
Okay. Once the solid is hot enough, like beyond that, it will not take any form of heat to raise its temperature. That state is called as saturation. Okay. Once the saturation is met, when the solid becomes saturated with the amount of heat it can hold, with the further amount of heat, if you start pouring into it, like if you still continue heating it, then that saturated solid will now start melting.
Okay.
Right? So the hot solid can be called as saturated solid. Once the solid is saturated, with the further addition of heat, this saturated solid will now start melting and it will become liquid.
Okay.
And during this process, the temperature remains constant. During this process, whatever the temperature this solid had achieved, this liquid will have the same temperature. It's like if ice is solid, like ice is obviously a solid, then maximum temperature of ice is?
If ice is solid, 0 degrees.
Solid. What is the maximum temperature of ice?
0 degrees?
Yeah. So H2O at its solid phase is ice, and the maximum temperature of ice is 0 degrees Celsius.
Yeah.
But when you heat the ice, it starts melting, and at that very phase, at that very state of the ice, when you still heat it, the ice will actually melt. And while the melting process continues, and if suppose you are continuously trying to build the equilibrium is basically like you're mixing the ice and the water, whatever is formed, then the temperature of ice and water will remain same. It will maintain the temperature of 0 degrees Celsius.
Correct.
And until unless the last particle of the ice is melted, the total temperature of the mixture would be 0 degrees Celsius.
Yes.
So that process is called as latent heating of ice.
Okay.
During the latent heating, the phase changes, but the phase changes, but the temperature remains constant.
Correct.
Okay. Now this is the lowest temperature liquid. Like water at 0 degrees Celsius is its lowest temperature state, right?
Yeah.
So once you start heating the water, now with the further addition of heat, this water will actually end up increasing its temperature.
Okay.
Right? And this state or this process of rise in temperature of the water will continue until it becomes saturated water. The lowest temperature water, and with the addition of heat, it will become saturated water. And the heat which you have given to the water in this process is called as sensible heat.
What do you mean by saturated water?
The saturated water is a state wherein if you still continue to heat the water, the temperature will not rise. Like in an open vessel, if you heat water, you will never find it above 100 degrees Celsius.
Yeah, correct.
right? So that is a saturated state.
That is saturated. Okay, all right.
Okay, this saturated state is a function of pressure, like at the sea level. At the sea level, like at your place, at Singapore, the level is almost near sea. So it will be near about 100 degrees Celsius. But the place
Yeah.
where I live is like, I think 400 to 500 meter above the sea level. Over here, the boiling point would be around 90 degrees Celsius, 90 or 95 degrees Celsius.
Okay.
So that is the state of saturation.
Okay.
If you are using a pressure vessel like a pressure cooker, in pressure cooker, the water, when it is heated, the pressure rises to pressure like 2 bar or 3 bar, and for that water, the saturation temperature would be 105 or 110 degrees Celsius.
Okay.
So that is the saturation state. When a water is heated from its lower temperature to saturation state, during that period, the temperature is changing, that as we can see, and such type of heating is called as sensible heating.
Okay.
Okay. And now the state would come, or now the value would come, which we can see over here, is basically latent heating of water. The latent heating of water, okay, the latent heating of water is basically when a saturated water is heated, it will end up converting into steam, right?
Okay. Yeah.
Will end up converting into steam. It's not like that immediately the entire water will get converted into steam or a vapor. It will take some time. It will take some magnitude of heat which will be required to convert it into heat, into steam. Like, in order to make sure that every particle of water is converted into steam, there will be some fixed magnitude of heat that you need to supply. That fixed magnitude of heat is called as latent heat of evaporation.
Okay.
That latent heat of evaporation will convert complete 1 kg of water into 1 kg of steam.
Steam. Okay.
Okay. So these are like 3 phases, as we know: solid, liquid, and vapor. And
Okay.
a heat which you supply for changing the temperature is called as sensible heat, whereas a heat that you supply to change the phase is called as latent heat.
Okay.
Okay. When it comes to use of formula for such process, for sensible heat, you can directly use mCpdt.
Okay.
M is the mass, Cp is the specific heat of that particular state. Like, like when you're converting, when you're heating ice, the Cp of ice is 2.1, as we had discussed in last lecture. And the dt would be the temperature rise of that solid.
Okay.
This formula can be used even for liquid when it is heated from its lowest temperature to its highest temperature. Okay. Over here, the Cp would be of water itself. Okay.
Yeah.
Okay. Apart from these two sensibility, even beyond the stage, beyond the phase of steam, like when entire water is converted into steam, it is like 1 kg of water, when converted into 1 kg of steam, it will have some temperature.
Okay.
Like this saturated water, which was at 100 degrees Celsius, when converted into steam, the lowest temperature of the steam is 100 degrees Celsius. Because this process is constant temperature. Beyond this, if you will heat the steam, the formula mCpdt can be used. Okay. Okay. Do you guys have steam table to solve such numericals? Like, or you need to, there is some standard table called a steam table, which is used to find the values of HF, HFG, HG.
No, we don't have that.
You don't have it. Like this value of HFG is actually obtained from standard table. Okay,
but I think maybe it'll be given.
Okay. During examination, or you guys don't have it like for yourself?
No, it is usually given. As you can see, most of the questions, they give us the values.
Okay, so maybe they will directly give you the value of HFG.
Correct, yeah.
Okay. Okay, so this was about this latent heat of evaporation. This latent heat of evaporation for 1 kg of water to convert into 1 kg of steam at atmospheric pressure is actually 2257.
Okay.
2257 kilojoule per kg. Okay. Once it comes into numerical, we will discuss it again so that it becomes clear. Okay.
Was it in the questions?
What?
Was this used in the tutorial questions?
I haven't gone through them. We'll see if at
Oh,
all.
it's okay.
Okay. So because they had given the formula, I just assumed that maybe there is a.
Oh, there you okay. Get it.
Okay. So this is about this thermodynamic term. Then flow regimes, they have given us the benchmark for laminar flow as we had discussed last time. Okay. Anything or any Reynolds number less than 2300 will be treated as laminar flow, whereas beyond 4000 will be treated like a turbulent flow. Okay. Sometimes in some cases or some in numericals, if they mention that Reynolds number less than 2000 is laminar flow, we will consider that. Okay.
Okay.
But since they have given you 2300 over here, I don't think so they will be giving you.
Okay.
Okay. This is entry length. Entry length, you remember? Entrance length.
Yeah.
The entry length is the length over which the fully developed flow is generated, right?
Yeah.
Where the velocity profile becomes parabolic.
Yeah.
Okay. So they have given us some formula in the form of laminar flow, then turbulent flow, in the form of Reynolds number and diameter. Okay. Why do they have given us 3 formulas? H stands for?
I'm not sure.
Okay. H. We'll see. Why have they given us the abbreviation of H and T? Like, how do they differ? This is in the form of Prandtl number. This is in the form of. Will you be having these values or these formulas in your examination? Because it is not easy to by heart them.
It's not easy to what?
It's not easy to actually mug up, to remember.
Like, I don't think it. They have
formulas that you need to know.
I don't think they follow exactly that.
Okay.
Can I just show you the exam paper formula sheet?
Yeah, it will be good.
Like more or less what it would look like. I think it will be this because it's past year paper. Just give me a second. Huh?
Okay.
This is what they gave in the paper.
Okay. What I think, this H is basically for hydrodynamic, whereas T is for thermal, I think.
Okay.
Because if you can recall, then we had discussed in the case of tube, where we had a discussion about the surface temperature and the fluid temperature, and then we generated a parabolic profile. Even in the boundary layer in the last lecture, we made a velocity profile for hydrodynamic, that is velocity. At the same time, we also made the same parabolic profile for the thermal boundary layer.
Yeah.
So I think this H is actually for hydrodynamic and T is for thermal.
Okay.
Okay. For now, we will just try to remember this, like H stands for hydrodynamic. And T stands for thermal.
Okay.
Okay. So basically they have kind of given us formulas for entrance length. Entrance length, when the flow is laminar, the pipe, if it is considered like this, and if you remember at the entry the velocity is same, and at a particular length a velocity profile in a parabolic shape was formed, that length is called as entrance length, right?
Yeah.
So for laminar flow, for laminar flow, the formula for hydrodynamic and thermal is different.
Okay.
It is equal to 0.05 times Re into hydrodynamic or diameter. See, so it is equal to Re 0.05 into R into D for hydrodynamic, whereas for thermal entrance length, that same value is multiplied by the Prandtl number. Right?
Yeah.
0.05 Re into D into Prandtl number. Okay. Why do they have equated it with Prandtl number? Now this formula it is not easy to understand what exactly it is. Okay, understood. So basically they have just replaced they have just replaced this above value over here, like whatever we were discussing, right? So it is Prandtl number into L hydrodynamic. Okay. And when it comes to turbulent flow, the hydrodynamic entrance length is equal to thermal entrance length, which is equal to 10 times the diameter. Okay.
Yeah.
So if at all it is needed, we will find it with this formula. How to find the entrance length? Maybe I think there was a question in those paper or the sheet which you had shown me to find the entrance length.
Okay.
Okay. So next is Nusselt number relation. Next is Nusselt number relation. The Nusselt number correlation for the Nusselt number correlation for fully developed turbulent flow, for fully developed laminar flow. Nusselt number and friction factor is cross section. Okay, this is the Nusselt number this is the value of Nusselt number. Directly they have given for fully developed laminar flow. So this is like 3.66 and 4.36. These are the two values for pipe with diameter D.
Okay.
And then for turbulent flow, you need to remember this formula of Nusselt number, which is 0.023 Re raised to 0.8 PR raised to 10, which is mostly 0.4 for heating and 0.3 for cooling.
Okay. This is standard, is it?
This is the relation for Nusselt number we need to use for turbulent flow numericals. So before we actually use this equation or this value, we must have to calculate the Re, Reynolds number. So knowing the value of Re when it is compared to 2300 or 4000, we'll get to know which exactly value we need to use.
And then you see whether it's turbulent or laminar.
Yes. Okay. It is not that easy to remember all these values. See, like for different cross section, for different A by B, there is different value of Nusselt number.
Yeah.
And that to see when the temperature remains constant, the Nusselt number is different, and when the heat flux remains constant, the value is different.
So I don't have to remember, this will be given to me.
It should be given to you, or maybe you'll have to use this table. For now, we can use this table for solving the questions which you have given us, which you gave me. But in examination, you might need this table.
Okay.
So this was about Nusselt numbers relation, which we need to use for solving the numericals. Like in our examination, in our university, they always give us this equation. This Nusselt number equation is always given. So it becomes very easy, very convenient to use it. It is always given below the numerical.
Okay.
And most of the time, or majority of the time, they directly give you two equations like Nu is equal to, simply writing the value equal to 3.66 when Re is less than 2300, when Re is more than 4000. So that's how it becomes convenient to use it.
Okay.
Right? Let's see. Let's see how it is given. Okay. So let's proceed.
What do they mean by that? Oh, so the N is always going to be 0.4 for heating and 0.3 for cooling?
Yeah. N is the power of PR.
Yeah, I know. So we have to follow the standard number of 0.4, 0.3?
Yes. Once the process is heating, then N is taken as 0.4. Like in a pipe, if there is a fluid flowing into it, and at entry temperature T1 is lesser than the exit temperature T2, then the process is heating. Then we will have to use N equal to 0.4 in that case.
Okay.
Because ultimately T2 is more than T1, it means it is a heating process.
Okay.
So that it is applied only to a fluid, the fluid over which we are applying this Nusselt number equation. Okay. So the next case is about constant surface heat flux. Entrance length, fully developed region. Okay. Do you see that delta T remains constant from here to here? Like starting from this point, you can see that delta T at this point is equal to delta T at that point.
Yes.
So whenever, and if you look at the formula, Q is equal to HA delta T. So if delta T remains constant, then such cases are called as constant heat flux cases.
Okay.
Okay. So whenever there's a question called saying that in this process, the heat flux remains constant. So ultimately delta T is constant from the entry to exit.
Okay.
Okay. And in that case, we will have to use for laminar flow these values.
Oh, okay.
Okay.
So what do they mean when temperature is constant?
Surface temperature remains constant. Like if there's a pipe in which fluid is flowing, the fluid temperature might change. Like at entry it was, let us say, T initial, and at exit it is T final. So if surface temperature is hotter, like surface temperature was maintained as 100 degrees Celsius from here to here, but the initial temperature from 20 to 50, right? So in this case, the fluid got heated and the surface temperature was throughout constant. So if we get numericals where the surface temperature never changes, we will have to use this value.
So the question will tell us, right?
Question will give us the case. We will have to understand and analyze accordingly. It will be our call that, okay, looking at the value, you can clearly see delta T means temperature difference between the fluid and the surface. You can clearly see that at entry Ts minus Ti is 80. It was 100, right? 100 minus 20 is 80. And at exit it is 100 minus 50 is 50. So delta T is not constant.
Yeah.
In initial case, which we were discussing, I told you that delta T remained constant. Whenever the delta T remained constant, the case is called as constant heat flux. But case where delta T doesn't remain constant is called as constant temperature surface case.
Okay.
Okay. So this is something we must understand and use accordingly as per the required numerical. Okay. So this was about constant heat flux case, constant surface heat flux, constant surface temperature. Okay. They have tabulated the difference in the formula. Okay. See, in this case, Q, which is equal to mCp delta T. E stands for?
end?
See, this is
And
T
initial?
and TE. E would be, what would be TE?
Is it initial and end?
Oh yeah, initial and final. T final minus T initial. Simply, okay, yeah. Whenever this formula of MCP dt is used, we should always remember that the delta T would be of the same fluid or same substance.
Okay.
Whenever the formula of MCP dt is used, this delta T or this temperature difference will be always for the same substance, which is getting either heated or cooled. When it comes to QA, when it comes to QA formula is this one. Okay, like HA delta T. Q is equal to HA delta T. Whenever we'll be using this formula, in this case, the delta T will be always the temperature difference between the fluid and the surface.
Okay.
Always. Okay. What is this? T end. Okay, they have simply substituted the value of T initial plus. Okay, I think they have kind of simplified this formula.
Yeah. They just rearranged it.
Yeah, they are rearranged. Okay. So I don't know if we have to use this formula, we need to use this formula, but yes, we can if you want. But remembering this formula is not that convenient. Rather, we would simply find the value of Q and equate it with this to find the unknown if required. Okay, so what would be the difference between the formulas? Okay, they have given us the formula of HA delta T ln. Do you know the log mean temperature difference? Have you ever seen this formula, log mean temperature difference?
I think so, but I cannot recall it.
Okay, do you understand?
I think you went through this with me a bit also, right?
No, that was a different formula. That was for the conduction.
Yeah.
That was for the conduction, and look at the terminology over here, it is convection. There's a terminology called as parallel flow and counter flow.
Okay.
Have you heard it before?
No.
Okay. See,
but I think it's something I need to know. Let me just check. I wrote it down. This is under internal, is it?
See, internal flow is basically a very generalized flow. In this case, there can be many combinations. There can be many different combinations, and then there are some heat exchangers which you must know before you actually proceed with the internal flow. Like there's a temperature difference or temperature distribution, which if I can show you would look like, see, suppose I'm drawing a graph for tube in tube arrangement.
Okay.
Tube in tube is basically a concentric tube, two concentric tubes wherein one of them is having a hotter fluid and one of them is having a colder fluid.
Okay.
Like in this tube, one of the fluid would be hotter, whereas there would be a concentric tube in which colder fluid would be flowing.
Okay.
Okay. So there can be two combinations in such cases where if you can see in this case, the fluid flowing inside the innermost is flowing in parallel with the fluid flowing, or maybe it is going in the same direction to the fluid flowing in the outermost tube. Whereas we can also have one more combination where let us say the entry fluid is going through the innermost fluid is going in the rightward direction, whereas the outermost tube would be having a fluid in the opposite direction.
Okay.
This arrangement is called as parallel arrangement.
Okay.
And this is called as counter arrangement.
Okay.
Okay. In parallel and counter arrangement, see, if you can understand, then I will just draw a graph which would show the temperature distribution of the individual fluids. Let us say in both the cases, we will take the inner fluid is colder one and the outer fluid is hotter one.
Okay.
So the graph for the first case, would look like this, and the graph for second case would look like this. Why? I will tell you, but yeah, they will look like this. The reason being, initially, when both the fluid were entering the system, this was the colder fluid and this was the hotter fluid, and they would have the temperature difference equal to the max value. And when they will start flowing, they will exchange heat. The colder will become hotter, whereas the hotter will become colder, and the delta T, the temperature difference, will shrink.
Okay.
So ultimately, the hotter will try to become like the colder one, and the colder will become like the hotter one, and the delta T at the entrance will decrease, and at the exit delta T would be least. I hope you understand this graph now.
Yeah, I do.
This is about the case wherein both the fluid are flowing in same direction. When they flow in opposite direction, like in counter direction, see, the entering cold fluid so the cold fluid can be assumed to be at this point. It is entering the system, and the hot fluid is entering the system in this direction. So I will just interchange the directions when you want to compare it with the graph. The cold one is flowing in leftward direction, whereas the hot one is flowing in rightward direction. See what will happen is, in this case, the colder one is again at the same temperature as it was in the initial case. Okay. The entry is same for both the cases. Whereas the hotter one is again at the same temperature for both the cases. Like the entry temperature for both the cases, I have assumed to be same. What will happen is that this hotter fluid will lose heat by exchanging heat from this fluid. Whereas this colder fluid will gain heat by raising its temperature. But the case is that looking at the graph, you should understand that at the entry, the colder fluid was in association with the hotter fluid at much lesser temperature than the case one. Okay. In case one, the temperature difference at the beginning of heat exchange was very high. And when there is a high temperature difference, the heat transfer rate is also very high. Okay. Like when there is when the gap between both the surface temperature is high, the exchange rate is very high. Okay. It's like when we get a very hot beverage, it cools very fast at the beginning of time. And when it kind of loses heat, the rate of emission of heat actually decreases with time. Okay. What would be the reason?
Because of the temperature.
Perfect. The temperature difference. Temperature difference between the two bodies, like the atmosphere and the beverage.
Okay.
In this case, the temperature difference was initially very high. Yeah. That's why exchange rate was very high. And when they continue the journey, you can see the delta T is decreasing. So the heat transfer rate will keep on decreasing.
Okay.
Okay. But in this case, initially itself, the temperature difference was not that high enough. In fact, whatever the temperature difference was there at the beginning was kind of same when they continue their journey of heat transfer.
Okay.
So in this graph, you can see that delta T at the beginning and at delta T at the end remains same.
Yeah.
Not exactly same. It will depend on the mass flow rate. It will depend on the type of the fluid which is flowing. But there is a chance that delta T at the beginning and delta T at the end can be same in this case. But in this case, it will never be a case where delta T at the beginning and delta T at the end would be same.
Okay.
Okay. Practically, this case is never preferred. In real life, always this case is preferred more. Can you tell me why? Can you think and tell me what would be the reason?
What is this instrument used for?
Okay. Geyser, water heater, normal condenser, evaporator. Have you seen any condenser, evaporator? What?
You do not want the temperature to change.
Okay, my question was, like we are having some radiator or condenser in our day-to-day applications. Like a refrigerator has a condenser behind it, right?
Yeah.
Or a radiator or condenser, anything, any heat exchanger, if they're using two fluids. Okay, I think you are aware of the heat exchangers. Do you understand the working of condenser?
Condenser, no, not really. No. But like water heater, you said, right? Or are you talking about normal heater?
Normal heater would be also okay. Look, condensers are just a mechanical device behind the air conditioner.
Okay.
The unit which is outside the house. It is condenser. The one which is inside the house is evaporator.
Oh, okay.
Okay. So these are also two heat exchangers. Similarly, even a water heater is a heat exchanger. But the case with water heater is there is only a single fluid involved. A water getting heated and there is an electrical coil.
Oh, okay.
So I cannot explain you like with a reference to two fluid losing their temperature or gaining their temperature. Okay. So like imagine you are having a water heater at home which is not using electricity but using steam or using some hot smoke.
Okay.
Okay. So it will be flowing through two concentric pipes where your water is flowing from inside the pipe and the hot smoke or the steam was flowing from the pipe which was concentric and outermost, right?
Yeah, so you wouldn't want to change the temperature, right, throughout? You want it to be constant.
I wouldn't want this case. I would want this case.
Correct.
I'm not bothered if the delta T at the beginning or at the end is different. How does it matter to me? Why would I even think of it as a user? But as a user, what is that one thing which is important for us, wherein I will prefer this over this? Just look at the graph and tell me if you can say anything. Just look at the end point of the, just think of your own application, like the water which we were using, and look at its exit temperature, this temperature and this temperature. Which one do you think would be more, the case 1 or case 2?
Exit temperature of water.
Exit temperature of water in case 1 and case 2, which would be more?
Case 2?
Yes, case 2. The reason being, the water which was coming outside the system will be in association with this hot fluid, and there will be heat transfer. and assume that you don't have any limitation to the length of the tube or length of the pipe.
Okay.
In that case, no matter how hard the water would try, it will never reach the temperature more than this temperature.
Okay.
Because they are in association. If the hot body and cold body are together, the cold body would want to become like a hot body. If you see this graph, the cold water will, if at all, become like hot water or the steam or the smoke, the max value it will attain will be somewhere over here at this point.
Yes, it
But
will
in
never
case
become.
two, if I increase the length of the tube, there is very high chance that this entry temperature might become equal to this temperature.
Why though?
If I increase the length of tube, if I believe that I have an infinite length tube, and if the water is flowing and exchanging heat, at the exit of the water, the outer tube is having smoke or steam at the hottest possible state.
Okay.
So in that case, it will still try to become like that hot smoke. Even if it doesn't become like that hot smoke, it will at least have a value much more than this value.
Yeah.
Because this hotter fluid has lost its heat and the temperature over here is lesser. But in this case, since the flow direction is opposite, this exit temperature can, there is a possibility that the exit temperature would be equal to the exit entry temperature of this hot fluid.
Okay.
So whenever you are trying to make your own heat exchanger, you're designing your own heat exchanger, you will never arrange the system in this way. It should always be in this manner.
Okay.
Okay. In both the cases, this entry temperature is taken as delta T1 and exit temperature is taken as delta T2. Over here also delta T1 and delta T2.
Okay.
Okay. Delta T is temperature difference between the two fluids. It can be same, it can be different. It can be same, it can be different. If at all delta T1 and delta T2 are same, then the formula of Q convection is simply HA delta T. HA delta T. Because the temperature difference at entry and exit is same. But if they are not same, if they are differing, the formula is taken as delta T logarithmic mean.
Okay.
Okay. This is something which they haven't mentioned over here, but you should always remember that if delta T1 at entry is equal to delta T2 at exit, the formula would be simply HA delta T. But if delta T1 and delta T2 are not same, like if they are differing even a bit, either in case 1 or case 2, whatever it is, the formula is taken as delta T mean, and this delta T mean is equal to delta T2 minus delta T1 upon log to the base E delta T2 by delta T1.
Okay.
They have also kind of written the same formula. Okay. Delta T2 minus delta T1 upon log to the base E delta T2 by delta T1.
Yeah.
Okay. This formula looks a bit complicated for me to remember. I would always prefer using this formula.
Okay.
Delta T2 minus delta T1 upon log to the base E delta T2 by delta T1. Okay. By mistake, if you write delta T1 minus delta T2, just remember to take the ratio also delta T1 by delta T2.
Okay. Then you end up same answer.
You will never go wrong. Like this is also equal to delta T1 minus delta T2 upon log to the base E delta T1 by delta T2.
So this is temperature mean, is it?
This is log temperature difference.
Log temperature difference.
It is log mean temperature difference.
Okay.
There are many basics and many such important concepts which I don't feel you guys are taught. It is assumed that you might be knowing.
Yeah. They assume you know it.
Yeah, it makes things very difficult. Like you must have seen that simply about HFG, there was a lot to know for you guys. simply
Yeah.
from this log mean temperature difference also, there's a lot to know. In our syllabus over here, they give you entirely a dedicated chapter for all these unit topics.
Oh, in the third year or in the first and second year?
For this topic, there's a dedicated chapter called as heat exchanger. And for the HFG topic, in second year, there's a dedicated chapter.
Okay. Maybe I missed the HRT, but they didn't have one for this, I think.
Over
Maybe they
there
did,
also,
but
there
they
would be a
moved
dedicated
too
chapter.
fast.
Over there also, there would be a dedicated chapter for that HFG topic because it is a very important concept in thermodynamics.
But maybe they moved too fast. I have to look through.
Yeah. I have seen many of the college professors are like, they assume that students must be knowing all these basics.
Okay.
Okay. Nevertheless, I hope you understood whatever we just revised and understood, learned.
Yeah.
Okay. So this was about delta T mean. Whenever it will be required, I'll just make sure that you remember and recall it. Okay, these were Nusselt number equations, and this was about. There are some formulas you must write them down, like Q is equal to HA delta T when delta T1 is equal to delta T2 for internal flow. And if they are not same, delta T mean can be simply taken, delta T log mean. And the delta T log mean would be delta T2 minus delta T1 upon log to the base E. Delta T2 by delta T1 can be taken as also delta T1 minus delta T2 upon log to the base E delta T1 by delta T2. What is delta T? It will be very convenient if you simply draw the graph like this is length versus delta T graph. Whenever the question would be given, we must draw, they see even they have drawn a similar kind of graph. If like two fluids are flowing, if the two fluids are flowing, one of the fluid, if it is flowing rightward, and if one other fluid is flowing leftward, even if by mistake you give them same direction, it will be okay, doesn't matter. Okay, so but in this case, let us say the direction is opposite. Now what is delta T? Delta T is basically, this is delta T1 and this is delta T2. Okay, and second case also I will draw. If suppose one of them is moving rightward and another is also moving rightward, the graph would look like this, and this will be delta T1 and this will be delta T2. Okay, this arrangement is called as parallel arrangement. Sorry, counter. This arrangement is called as counter, and this arrangement is called as parallel. Okay, I will kind of take a snapshot. Okay, maybe while looking at the recording, you take a snapshot. Okay, because whenever I write on the PDF, it doesn't come as a snapshot. Okay. Okay, so this was about the basic formulas that we'll be using. Okay, one more thing, delta T mean. Delta T mean is average temperature. Average temperature. See this formula. Now, this is something which might confuse students. Like, why are they using here some different formula, whereas over here some different formula? What do you understand by this term? What is it? Delta T is equal to delta Ts minus delta Tm. What is Tm? The mean temperature. Yes, the mean temperature of these two values. Okay, so T mean would be TE plus TI by 2, right?
Yeah.
And delta T will be equal to TS minus delta T mean.
Okay.
So which one should we be using? This delta T or delta T log mean? What do you think? Okay. If you want more accurate value, this formula will always end up giving you correct value. Whereas this formula will always give you approximated value.
Okay.
Okay. Sometimes the numericals are so big, so complicated that getting the exact value is never the priority. Even approximated or average value will do. So in that case, or in those cases, many a times authors use this formula.
Okay.
So, but in your case, if it is like you want to use this formula at every instant, even that will do.
Okay.
Okay. Or you can remember it like this, that if there's a case when two fluids are flowing, one fluid is flowing in innermost fluid and another fluid is flowing in outermost fluid, then always use delta T mean.
Okay.
And in another case, when only single fluid is used and the outer temperature throughout remains constant, outermost temperature throughout remains constant, there will be using this formula.
Okay.
Right? So if it is like two fluids are flowing, use delta T mean. If one fluid is flowing and outer surface is maintained maybe by electricity or by some steam or by some different source at a constant temperature, we will be using this formula, Ts minus Tm. Okay?
Yeah.
Okay, what does the log mean temperature difference represent? See, they have even asked you the question.
Yeah.
What would be your answer? What do you think? Just tell in your own words. Okay. When you have to answer this question, do always try to draw the graph which I had drawn. Okay.
Oh, we have to draw?
Draw those graphs like parallel and counterflow.
Okay.
Then explain them about the delta T, how it is changing. You'll have to explain that in parallel flow, the delta T decreases continuously, whereas in counterflow, the delta T does not change that significantly, or in few cases, or in some of the case, it might even remain constant.
Okay.
Okay. And also you can explain that in counterflow, there is a possibility that the exit temperature of the colder fluid can be equal to the entry temperature of hotter fluid.
Okay.
But this can never be a case, or this can never be, but this is impossible to attain in parallel flow.
Okay.
Okay. And then you can explain that to find the heat transfer rate for case where the temperature difference between the two fluids are continuously changing, an average value is found by taking the log mean temperature difference.
Okay.
Why do we use the logarithmic? See, they have kind of asked you the same question which we were discussing now. Why do we use the logarithmic mean temperature difference instead of arithmetic mean temperature difference?
Because you don't get an exact value. You get a rough value, right?
Yes. And then you can explain that whenever there will be two fluids flowing, always prefer logarithmic temperature difference. Whereas when there is a constant temperature surface, we can go for arithmetic mean temperature.
Okay. So how would I put it in words? Like if I want to say that one is more accurate than the other, you just say that?
See, the difference is practically when they are saying logarithmic, it means it takes difference at every instant. It's like an integration of differences.
Okay.
See, I will try to explain you that this is something that goes without saying. It's like when you take end-to-end differences, it is not bothered about how the slope would be.
Mm-hmm.
But in logarithmic temperature difference, what it does, it takes temperature difference at every instant.
Okay.
It is like it is calculating delta T at each instant and then giving you the average value.
Okay.
This formula, the formula which you can see about for the logarithmic term, this formula is obtained by taking the integration, by the way.
Okay.
It is like you take a very small thickness of the tube, you find the delta T for that very small thickness, and then integrate it for the entire length of the tube. And automatically the simplified formula is in the form of log.
Mm-hmm.
So it is like it is taking a small divisions and finding the heat transfer rate for every small divisions. So that's why it is more accurate. It is like you're sampling it into small divisions.
Yeah.
Whereas the arithmetic mean is basically just bothered about end-to-end conditions. Are you getting me?
Yeah, I'm getting it.
Okay. So let's go through the questions now.
Okay.
Okay.
Can we take a 5-minute break?
What?
Can we take a 5-minute break?
Yeah.
Okay.
And feel free to ask any question. Okay. Never just simply nod because I have kind of completed it. Because there can be a situation like I have seen myself under pressure. Students are like, okay, I understood. Maybe I'll just think and I shouldn't sound dumb. So if there is any such case, just let me know. I will try to explain with some different example. Okay.
Okay, sure.
It's very normal. It is very normal if you don't understand things. Just ask me in your own way.
Okay. Can.
Take a break. Take a break.
Thank you. Like I'll be back in 5 minutes.
Yes. Okay.
To record. Thank you.
I would recommend, you should go through all the questions, like each and every question, whatever the questions are given in this topic.
I will try to go through them myself also, and then I can ask you again when I see you in the next class.
See, like in this case, this is one of the question. Okay, there are many questions. Like, would you want to solve these questions or those questions which you have sent me?
I think we do everything. Is that okay?
Yeah, no issues.
Yeah, on based on internal pipes, measure connection, and radiation.
Okay, we'll
do you think we covered?
Go through all the questions, like theory questions also, a numerical question also, and I'll explain what theory question you need to explain, and we will solve the numerical question also.
Okay.
Okay. See, I think in this case we have gone through the required formulas, and these are 2 theory questions you must be explaining.
Okay.
Select some more points from some notes or some textbooks if you can, and if you don't understand any point, just ask me.
Okay.
Okay. Like I don't know how theory papers are there over there. Like over here, we write point wise the answers as much as possible. It should be in limited points, and you shouldn't be going beyond 5 to 6 points, and draw a graph or a diagram if possible.
Oh, okay. So right now the exams are still based online. So because of the COVID situation.
Okay.
Yeah. So we have some, I think we have to type it out maybe. I don't think we have to draw a graph.
Okay.
Or maybe we have to like draw everything on paper and submit a copy of it. Either one. Yeah.
Okay. Still there are online exams in Singapore. Okay.
Yeah. They are phasing out. They are slowly moving. But for this semester still.
How's the COVID situation over there?
Still bad. There's still, I think more or less everyone has it also. Yeah. Lots of kids are getting it also.
But schools and colleges are still going on, right? Students are going into schools.
Going on, yeah. But if they catch COVID, then they will isolate them and they can't return to school for a while.
Okay. Things are better over here then. Quite better. Okay, like all the schools and colleges are all open, and I don't think so people are even bothered about the cases now.
Oh, yeah. Here, I think because one of them gets it and then a cluster of them in the class gets it. So
Okay.
then that whole class has to go online.
Oh, whole class goes through online then.
Yes.
Okay. Maybe that's why people over here don't tell about the COVID case. Let's face it ourselves and not tell anyone. It's like that. And now it is just a matter of 2-3 days. Like it's like a normal flu, and people just get cured.
Yeah, we get better eventually. But I think recently 2 children died. So
Oh,
in Singapore. Yeah. So I think that's why.
okay. That's sad.
Yeah.
Okay, let's go to the question. Okay, we just discussed these 2 questions.
Mhm.
Now this is the question, numerical question. A cooling water available at 10 degrees Celsius is used to condense steam. It's an important word, condense steam at 30 degrees Celsius in the condenser of power plant at the rate of, this is mass flow rate, by circulating cooling water through a bank of 5 meter long. Okay. 1.2 centimeter internal diameter, thin copper tube. Water enters the tube at mean velocity 4 meter per second and leaves at a temperature of 24 degrees Celsius. Tubes are isothermal at 30 degrees Celsius. Determine the average heat transfer coefficient, means H, and the number of tubes need to achieve the indicated heat transfer rate. Heat of evaporation. Okay. Good. So, what did you understand? Looking at the diagram also, it is self-explanatory.
Yeah.
Water enters at 10, it leaves at 24. It is surrounded by steam at the periphery, right?
Yeah.
The steam condenses at 30 degrees Celsius.
Mm-hmm.
It means the steam will remain 30 throughout.
Okay.
So the T surface is 30 degrees Celsius. T mean would be 10 plus 24 divided by 2.
Okay.
Okay. Just give me 1 minute.
Yeah.
Okay. So
here you took T mean as final temperature minus initial divided by 2 because why?
Okay, that's the question. Okay, see, whenever there will be a case where not another fluid is flowing, and if it remains throughout at a constant temperature, we can take the relation of delta T is equal to Ts minus T mean. And in this case, Ts is 30 degrees Celsius. Surface temperature is 30 degrees Celsius. The tubes are isothermal at 30, they have said. So it's like the tube outside surface remains 30 degrees Celsius throughout every instant.
Oh, okay.
And then
so because there's no temperature change.
No, it will not have any temperature change. It is like steam at 30 will get converted into water at 30. It's an isothermal process.
Okay, so that is why we use the arithmetic mean.
Yeah, if you want, you can use the logarithmic mean also. Okay, the answer would be same, almost same. Doesn't matter. But the thing is, this will give us the value faster.
Okay.
But believe me, mathematically, it will not change anything. You will have kind of similar answer. Okay, see, like T mean would be 24 plus 10 divided by 2. Do you have a calculator?
Yeah, I do.
Okay, just tell me what would be the delta T. 30 minus 34, 13?
Yeah, 13.
13. Okay. Let's try to calculate logarithmic temperature difference. Delta T Lm would be delta T2 minus delta T1 upon ln delta T2 by delta T1, where delta T1 would be 20. No, this would be 30 minus 10 equal to 20, and delta T2 would be 30 minus 24 equal to 6. Take a 20. The formula would be then 20 minus 6 upon log 20 by 6. Use the calculator.
Change in temperature 2 is between water at the end and the end beginning.
Okay,
No.
it is always the temperature difference between the two different fluids. So this is the temperature difference between steam and entry water. This is steam and the exit water.
Oh, okay.
Okay. Now just use the calculator and tell me what is 20 minus 6 upon log to the base E20 by 6.
$11.6.
Yeah, see, approximated.
Okay.
That's how it will differ.
Okay.
Looking at the formulas which they have given you, I think for your case, you will have to follow this formula, because even though if you use this formula, the answer would be approximately same. This is the more accurate value, but sometimes the questions are only generated so that you use the formula which they want you to use.
Okay.
Use this formula only when two fluids are flowing. Use this formula when surface temperature is constant.
Okay.
See, surface temperature at 30 was maintained over here. It will be 30 from here to the entire length of the pipe. Okay. So
yeah,
if you have a solution for this, do you have solutions being given for this?
Yeah, I do. I think I sent you the last time.
Okay.
Should be tutorial 7 then, I think, or 5. I'm not.
Just cross check what they have used. Tutorial 4, right? Or 5?
No, not 4.
Internal.
5 is external.
5.
You only have a
No. We don't have. You have sent me only 4.
7. Okay, let me check on this.
You sent me only until the external flow. Like,
okay,
maybe it would be the tutorial 7 or 8. You had sent me tutorial 2, 3, 4, 5, 6.
Let me check. Yeah, they don't have. Oh, they do. They do. Let me try. It's taking a while because the internet is bad here. Give me a second.
Okay, tutorial 7 and 8. Okay, they do give you formula sheet for the exam.
Yeah, they do.
Yeah, this will make life easier.
Okay.
Yeah, see, seriously, you can't remember all the numbers. It's not easy.
Yeah.
Practical.
I might fail.
Anybody would fail. Even I might fail. It's taking a while to download.
Okay.
Okay. Yeah, I got the question. 7.2. Something is wrong
Okay.
with the values. They have taken exit temperature 80, but over here it is given as everything is different. No, sorry. 7.2 they have solved somewhere else from somewhere else. The 7.3 is the one which we are looking for.
So we are, yeah, I think.
Oh, they have solved it by delta T ln. Thank God we saw this solution.
Yeah.
What are they expecting? Like, then why have they given us those formulas?
Yeah, because they don't use it, right?
They don't use the arithmetic mean anywhere.
So far, I don't see it.
I also don't see it. Okay, we don't have problems with that. But the thing is, they shouldn't be having that formula in their examination as their reference formula. Because ultimately, it is not about the concept. The concepts are same, but using different formula might end up having a wrong answer. Okay, then we will also use the log mean temperature difference.
Okay.
The log mean temperature difference.
Which is the one we did just now, 11.6?
Yeah. You understood how to
Okay.
use the formula, right? Like the delta T.
Yeah.
See, like
You explained just now.
see, for me, like when I refer to such questions, I always prefer drawing the graph because that makes things easier. For now, like if I draw the temperature lines, the 30 degrees as a steam temperature will not change. So it will be a constant temperature line. But the fluid in contact will have its temperature rising. So it will go like this. Okay, so this is 30 over here and then 30 over here. It is 10 over here and 24 over here. It will be really convenient for you also if you prefer drawing this. You will never go wrong with the formula then. Then like over here, this will be delta T1. This will be delta T2. And the formula would be delta T2 minus delta T1 upon ln delta T2 by delta T1. So the value was delta T2 is equal to 6, delta T1 is equal to 20, and this way ln 6 by 20. Had you written this in the form of 20 minus 6 upon ln 20 by 6, even that will give you the same value.
Okay.
Because log has this relation, if it is the ratio of number less than 0, then the value is negative. Okay. Like ln 6 by 20 will be negative and ln 20 by 6 will be positive. Like in the numerator, 6 minus 20 will be negative 14, like negative 1,4. And in the denominator also it will be negative. So negative gets cancelled out and you will get a positive value 11.63.
Okay.
Right? So this is small information. You must know that it doesn't matter if you write 20 by 6, 20 minus 6 or 6 minus 20. Just make sure that in denominator it is in the same sequence.
Okay.
Okay. So now this was about logarithmic mean temperature difference. Okay. Now next thing is we need to find average heat transfer coefficient. Means you need to find the H.
Yeah.
Okay. In this chapter, the H will be always calculated using the Nusselt number relation. It will be Nusselt number which will give you H. Okay. Whenever there will be this value of HFG or whenever there will be phase change, Q equal to M HFG will be used.
Okay.
Q equal to M HFG would be used. M would be the mass of that fluid which is getting condensed or evaporated.
Okay.
So the M would be for mass of steam. Have they mentioned anywhere the mass of steam?
It might be below.
Cooling water at 10 used to condense steam at 20 of a bubble at the rate. Okay.
Is it under the properties?
No. The question is, this mass flow rate would be for water or would this be for steam? I think this is for steam. It is the steam which is condensing at 0.15 kg per second. You know why? Because they have given us the mass velocity of water. So velocity of water can give us the mass flow rate of water. From there, we can find the mass flow rate of water.
Okay.
Okay. So this is the mass flow rate of steam.
Okay.
So we can find the total heat lost or total heat absorbed by the steam by using the relation 0.15 into 2431. Are you getting me?
No. Why do you take the mass as 0.15?
They have given us the rate of 0.15 kg per second.
So that is mass flow rate, is it?
This is the, see, read the sentence. Is used to condense the steam at 30 degrees Celsius in the condenser of power plant at the rate of. So it is the rate of condensation. Okay. Rate of condensation is like every second how much amount of steam is getting converted into water.
Correct.
Every second 0.15 kg of steam is converting into water. So the mass of steam converted into water into the heat required to convert is HFG.
Yeah.
Q is equal to MHFG, right? You remember this formula?
Yeah, I remember the formula. But why is mass 0.15? That is mass or mass flow rate?
It will always be mass flow rate.
Oh, okay.
It will always be mass flow rate, m dot. Okay. Mass will always come into picture where there is some body which is not flowing.
Okay.
Like a solid plate or like a disc or some solid body which is losing heat or gaining heat, but it is not flowing. Only in that case there will be a term mass.
Mass. Okay. Yeah.
I think in your first chapter I had seen some question where they asked you to find the time required to cool the body or time required to heat the body. Or in how much second the entire body will get cooled. Something like that is asked.
Okay.
Solve those questions. Chapter 1 questions, have you solved it? No.
No.
How are they taking examination? Why are you checking these chapters first and now those chapters?
Yeah, because those were covered already. These are the chapters that are coming out next.
So you have given the test on the chapters already.
Sorry again?
You have given the test on those chapters already.
Yeah, the first half has been done. This is the second half that needs to be done.
Okay.
But they haven't given us the questions for this section. They have only given us like sample questions that might come out. And I found a past year paper based on this section.
Okay.
Yeah, that's all I have for now.
No issues. We'll just solve them all.
Yeah.
Okay.
That's why I need to focus on this section first, more than the first one.
Understood, no issues. I was like, why are we going through this chapter if those chapters are not covered yet? It's okay. See, what are all the formulas we must be knowing? We will discuss them. And how's the question flowing? We'll go through that. Okay, instead of solving it over here, I will prefer writing it on the whiteboard.
Okay.
Okay, so the question is, there's a tube. Tube is maintained at 30 degrees Celsius. It is having a fluid entering at 10 degrees Celsius and leaving at 24 degrees Celsius. There's some length of the tube. And then there is a diameter of the tube. 10 degrees Celsius, 24 degrees Celsius, 5 meter, right? Length of the tube was?
Yes.
Length of the tube was 5 meter and diameter was 1.2
cm.
So we will write it as 0.012 meter, right?
Yeah, correct.
Divided by 100, yeah. So it is entering at 4 meter per second. We will assume it to be constant.
Okay.
4 meter per second is the average velocity or the max velocity?
4 meters per second is mean velocity, average.
Average velocity. Okay.
Yeah.
So what are all the formulas we must be knowing for such question is, like, for convection formula, Q will be equal to HA delta T mean. Okay. Q equal to HA delta T mean, where H is coefficient of convection, A is the cross section area of the pipe. Right?
Yeah.
Delta T mean is the average log with temperature difference. It is equal to delta T2 minus delta T1 upon ln to the base delta T2 by delta T1, which we calculated. It was equal to 11.63 degrees Celsius.
Yeah.
Okay. So if we get the value of H, we can find the heat transfer rate, or either way, if we get the value of Q, we can find the value of H. Either way, it is possible.
Okay.
Right. Okay. So they have given us HFG. They have given us mass flow rate of the steam. So even that formula can yield us Q. Q is equal to M. Okay. Now Q will be written in the form of specific heat for two cases. One would be M Cp dt for water you can use, which is flowing inside. Also, this formula can be written as M HFG for steam which is above the pipe, which is getting condensed. Can you make the difference?
We can use either one of them.
You can use either of the formula, where M dot would be the mass flow rate of the fluid which is flowing inside. Okay, M dot will be mass flow rate of the fluid which is water which is flowing inside. Cp would be the water or the fluid which is flowing inside Cp, specific heat. dt would be the temperature difference 24 minus 10. MHFG would be for the fluid which is getting condensed. They have given us the mass flow rate of the steam, which is 0.15. Yeah, 0.15.
Yeah.
Why can't I see the value? Okay, 0.15 kg per second.
Yes,
okay.
Time 2431.
Kg was
2431. Yeah.
Okay. So this will be the total heat absorbed by the steam. This can be equated to this formula also. Okay.
Okay. So should I try out the other one and see if it works?
Yeah, we can.
So in this case, delta T will be?
Okay. This
24
formula?
minus 10, 14, is it?
Yeah.
Or it need to be in Kelvin?
Doesn't matter. The difference remains same.
Okay.
What are you taking the value of M dot?
0.15.
No. This is the m dot of the water which is flowing. So this won't be 0.15. This will be equal to rho AV. Rho they have given us. How much is the rho of water? 998. 998.7. Area would be area of cross section of tube. Pi by 4 d square.
Sorry, how did you get 998?
Properties.
I got 894.
Hold on. I will share the value. Stop sharing. Share properties. 894. Sorry, my bad.
Okay. 894. So it's rho AV, right?
Rho AV. CP? CP looks wrong to me. Water doesn't have CP of 1838. It has 4.187. Something is wrong with
AV
the
is the oh, is it?
Okay. I think the given data is wrong. The properties
Okay.
the properties given to us are wrong.
It could be there was some error when he was going through as well, the lecturer, I think.
Because CP of water is not 1838. It is 4.187. Also, just look at the solution which they have given. In that solution, they have taken 4.184.
In the solution, Yeah, and then they took
And they have taken density also 998.7.
998, yeah.
Okay.
So they just use their own values here in the solution. Maybe I'll just use that values as well.
Yeah, use this value only 998.7 and 4.184. 4183.8. Just make a correction in this.
So when they say area, they're referring to cross-sectional area of the pipe,
Yes.
right?
Yes. Okay. 998.7 into pi by 4 d square into velocity 4. How much is the value of m mass flow rate?
18,072. Oh, I did not change units. I'm sorry. Calculation error.
Okay. Just take these values. This is the density, this is the cross section, and this is the velocity.
Yeah. Zero 0.41451.
Okay. Okay, just try to understand. This is the This is the mass flow rate. This is the mass flow rate of a water. This is the mass flow rate of a water which is entering in a tube and getting heated to 24 degrees Celsius.
Correct.
Okay. If I put this value over here, then value of Q is equal to mCp dt. This is the M, 0.4518. Cp of water is normally it is 1.37, but they have taken something different, 0.4183.8. 83.8. Okay. 83.8. It is in joule per kg Kelvin, and dt is 24 minus 10.
Yeah.
Okay. Now tell me how much the value comes for Q.
$26,463.
26,463. 63. Point anything?
0.444.
0.44. Now this is in joule per second.
Yeah.
Okay. See, now we calculated the Q for water. Now let us do the similar calculation for steam. Okay. So this was for water. Now let us do it for steam.
Okay.
Because we have the value of mass flow rate and HFG directly, we just have to just multiply them. So it is like Q for steam would be m dot HFG, where m dot is 0.15 and HFG is 2431. Now it is in kilojoule per kg. Okay. Kilojoule, whereas this was in joule. So to compare it with, I will multiply it by 1000.
1000, yeah.
So now it will be also in joule per second.
Yeah.
Okay. Now tell me what is the value.
$364,650.
364,650.
Yeah.
Joule per second. Just compare the two values. Like it has got 5 digits, so it is like 26,463, and it has got 6 digits, so it is like 3,64,000. Clearly this value of heat is more than this value of heat.
Yeah.
What does it mean?
It's increasing.
No. See, whatever the heat is given by water, like whatever the heat is given by steam, is equal to the heat absorbed by the water.
Correct.
But still we can see that the value of heat being absorbed is much lesser than the value of heat being given.
Yes.
Water was flowing through. So this is for a single pipe. Right? This value is for single pipe, but this steam is like for entire steam.
Yeah.
For entire steam. And they have also asked us to calculate the number of tubes required in order to obtain these results.
Yeah.
So it would be like, the real case would be like there must be many tubes. There must be many tubes around. N number of tubes.
Yeah.
Water is entering and leaving at 10 degrees Celsius and 24 degrees Celsius respectively. Right? So it is like steam is around these tubes. Okay. And water is entering at 10 and leaving at 24.
Yeah.
The total heat being given by the steam is this. Steam has given like 3.646 into 10⁵ amount of heat. And each tube has taken this much amount of heat.
Okay.
So I think it is very easy to calculate the number of tubes now.
Just divide, right?
Yes, simply you can say that total heat given by steam would be is equal to heat taken by one tube into number of tubes.
Okay.
Right? We can say that total heat given by steam will be equal to total heat absorbed by all
Water.
tubes with water.
Okay.
All tubes with water. All signifies number of tubes. So it will be like Q. If this is Q total, if this is Q total, this will be Q total. And this is Q single. So Q total will be equal to number of tubes into Q single. So this will be like 364,650 is equal to number of tubes into 2646.33.
Yeah.
26463.
3.44.
0.44.
Yeah.
Just calculate the N from this equation.
Yeah.
Tell me the value, how much is it?
$13.77.
13.77, that is equal to 14 tubes.
Yeah.
This is one of your answer. Okay.
Okay.
They had asked you number of tubes and they had also asked you coefficient of convection H. Okay.
Yeah.
Okay. Now in this case, how to find the coefficient of convection? What do you think?
You need to find H. We know A and we know T mean and we know Q. So we just substitute in to find it.
Yeah, simple. So we have it all. All we have to do is simply just equate the values. Which one to equate to? HA delta T LM, should it be equated to this value or should it be equated to this value? Like, should it be equated to Q of a single pipe or Q of all the steam?
All the steam.
No. This has got a relation for a single tube convection. It is talking about the single tube, right?
How do you know? How do you know it's about the single tube?
Okay, simple. In this case, the A is for surface area.
Okay.
A is for surface area because convection has the surface area as a formula.
Correct.
Convection has surface area. If you will take surface area, what would be the surface area? Pi dl?
Pi r square.
No, that is cross section.
Surface area.
Circumference into length.
Circumference times length. Yeah.
Yes.
Pi
dl. So pi dl will have a length of 5 meters.
Yeah.
So pi d of a single pipe and length of a single pipe.
Okay.
Right? So ultimate surface area of a single pipe.
Oh, okay.
Because the area would be for a single pipe. That's why the Q would be for a single pipe.
Okay.
Okay, makes sense now?
Okay. So forever, the area is always of a single pipe for this equation.
Yeah, we cannot calculate the surface area of all the pipes. That will be like, in that case, if at all you are substituting the surface area of all the pipes, then you can equate it with this.
Okay.
See, now you have all the pipes. You have all the pipes. Now simply you can multiply that pi dl by 14. If you multiply pi dl by 14, it will be the surface area of all the pipes.
Okay.
It is one and the same, right?
Yeah.
So if you are substituting pi dl, that means the formula is signifying a single pipe. And had it been surface area of all the pipes, you would have substituted Q for all the pipes. Now make sense?
Yeah.
Okay. So we have the value of Q, which is 26463.44. Okay. Pi dl would be pi into 0.012, length would be 5. pi dl.
Mhm.
Delta T mean we have it already. Just calculate the value of h from the formula.
Okay.
Then
Working on it.
how much did you get?
Still working on it.
Okay.
So sorry, give me one. I'm quite
It's okay.
slow.
It's okay. I hope you're doing it on your mechanical calculator and not your mobile.
No, I'm doing it on my calculator.
You guys have this calculator, a scientific calculator.
Yeah. Just a different model, I think.
26463.44 divided by pi into 0.012.
I got 6035.80. Am I right?
11.63. It is
I don't think I got it. Why didn't I get it?
okay. Mine is 12071.
I got a very big number. Is it because I'm supposed to divide something by 1,000 or times by 1,000?
Oh, no. I have already given you all the values. See, the numerator is 26463.44 divided by pi dl into delta t mean.
Your pi dl is pi times 0.012 times,
Into 5.
right? Why into 5? Into 5, yeah.
Pi dl, right?
Yeah.
And into delta t, which is 11.63.
Give me a second, huh? Yeah, can I show you what I have and let me know
Yeah,
if
just
it's
show
wrong?
it to me on the camera. Like this.
Oh, okay. Oh, like I got this. Can
Okay.
you see?
I think you have a green screen effect. I can't see it.
Oh, sorry.
Okay. Take a snap if you can.
Okay. Like I solved out the pi dl, you know. What is your diameter?
0.012.
Oh, that's not the radius?
No, that's the diameter.
Ah, I took it wrongly then.
That is where it is.
Yeah. I thought that was the radius.
Yeah. That is where you went wrong. Otherwise, things are right.
Yeah, but I got like 12,071.
Yeah, that is correct. That's the answer. 12,071, right?
Yeah, but then the answer sheet says like 12.1.
Because it is our value is in watt.
Oh,
Watt
okay.
per square Kelvin. They have simplified it into kilowatt. So that will
Do
be
we have
12.071 kilowatt meter square Kelvin.
Must we change it?
Yeah, we can change it. Doesn't matter. If you write it in the form of that, even if the teacher understands the unit, it will be given correct.
Okay.
It is correct. It is correct. No issues.
Okay.
Okay. So first question is done. Let's go for another.
Okay.
Okay. Question 2.
The
What is
unit
it?
is kilowatt
We have also asked
per.
you the bulk mean temperature that the property of what is wrong with these people? The question doesn't talk about air and they need to ask me something about air. Maybe they must have copy pasted wrong data from a wrong question. This entire value of properties and this line belongs to some other question.
Maybe it's just shifted.
Oh
They
yeah.
edited it. It's all wrong.
If you see in the solution, they have given a solution for numerical in 7.2, wherein in this case, there isn't any numerical in 7.2.
Yeah.
So they must have simply copy pasted the
Correct.
over 2. Okay, no issues. Let's go to another. We can solve this also question, right? This one, the hot air.
Yeah. Okay.
You want to go through all this theory question? Plot the temperature profile in the fully developed. We have gone through this. Fully developed region only of a tube.
Yes, correct. Let me write it out. Is it okay if I write out questions that I have prepared for myself, and then if my solution, you just take a look and see if I'm wrong anywhere.
Oh, no issues, no issues.
Okay, I'll do that then. I'll try to get it to you by Wednesday night latest.
Yeah.
Okay.
Whenever it is convenient for you, just write it down and just send me a snap and we will go through it if it is correct or not.
Okay.
Okay. Will the heat flux be higher near the inlet or near the exit or circuit for laminar flow? What if the flow is turbulent?
We can do the 7.6. I'll do the theory myself.
Okay.
Yeah.
Hot air at atmospheric pressure and 85 degrees Celsius enters the 10-meter long uninsulated square duct of cross section 0.15 into 0.15 that passes through the attic of house. Okay, volume flow rate is also given. The duct is observed to be nearly isothermal at 70 degrees Celsius. Okay, determine the exit temperature of the air and the rate of heat loss from the duct. Okay, looks straightforward.
So first I have to find Q, right?
They have given us Q. Okay, sorry. They are asking us heat flow rate, correct? See, the question says this is the duct. Yeah, it is kind of similar to the previous question. Instead of water, now air is flowing. Instead of velocity, they have given us now discharge. That is volume flow rate.
Yeah.
Mass flow rate formula is rho A into velocity, where this is volume flow rate, by the way. So if they give you volume flow rate instead of velocity, simply multiply it by density and get the mass flow rate. The density is this much. It is 0.9994 into 0.1, and now this will be in kg per second. Because if you simplify the units, this is kg per meter cube and this is meter cube per second. Meter cube gets cancelled out and the unit is kg per second. Right?
Yeah.
These are some small adjustments you will understand with numericals, with practice. Okay. So this was mass flow rate, which is calculated. Okay. We can find delta T mean. Delta T mean would be delta T2 minus delta T1 upon ln delta T2 by delta T1. Okay, now what would be delta T2? We can draw the graph for convenience. It is maintained at 70 degrees Celsius throughout. And the air is getting heated. Oh. Hot air is entering, right?
Yeah.
So it is getting cooled. So it is getting cooled. So I will draw this 70 line below. And the hot air is getting cooled like this. So this will be 70 throughout. 84 degrees Celsius air is entering. And this is question mark.
Yeah.
Okay. Using this formula in this situation will make things complicated. We'll just wait because we don't have this temperature.
Yeah.
So just wait and watch. We will use it if at all we are able to find the temperature. So next thing we can do is we can use the relations. We can use the formula of mCp dt. Q equal to mCp dt of air. M of air we already have it. Cp of air also they have given us. So it will be like this value can be like 0.09994 into Cp value is 1008 and dt value is 84 minus T final. If this is T initial, let us say this is T end. Okay. So 84 minus T. In this formula, if somebody gives me Q, I can find TE. All I want is Q. So Q cannot be calculated by this relation. How else can we calculate the Q?
Mass flow rate times the HFG.
HA delta T.
Oh.
HFG we cannot do it because in this case there is no phase change. In this case, they haven't said the air is getting condensed outside or getting evaporated outside.
Okay.
In previous case, the steam was getting condensed. So we knew that what exactly outside is happening. But in this case, they haven't mentioned anything about outside scenario.
Okay.
So outside condensation or evaporation is something that we can't do over here. So we are left with only one formula, that is HA delta T. Okay.
H what T again? Sorry.
HA delta T, convection formula.
Oh, the HA change of T, is it?
Yeah.
Okay. So we find that.
How did they find the TE? They have used some relation for finding the TE. TS minus initial raised to E minus HA MCP. Okay. Have you gone through a theory concept called as NTU method, number of transfer unit method? Have you heard it anywhere?
No.
Okay. These people are pathetic. What they do, you know, they simply use the formula without even talking about it. So it like, I know the concept, that's why I know what exactly they have done. But for students, it will make them
more confused.
Curious. Like, how could they use a formula to find TE directly? Okay, that is something which is not convenient, and it's altogether there's a lot to teach. Okay, so the relation is like TE is equal to TS. Okay, we will simplify the formula we have used, and maybe I will try to teach you in the different manner, like not the entire theory. but the formula they have given us, I will try to simplify for you. They have given us a formula. TE is equal to TS minus TI raised to E raised to, sorry, into E raised to minus HA surface upon MCP. They are using this formula to find the TE. Okay. I will just take this on the other side. So this formula will look like TS minus TI into E raised to minus HA upon MCP is equal to TS minus TE. I've just kind of exchanged the terms. I've taken this on the right side, this on the left side. Okay. Now I will take this in the denominator. This will look like E raised to minus HA MCP is equal to TS minus TE upon TS minus TI.
Okay.
Okay, so this is the one of the relation
that they used,
which they have used and directly simplified to find the T end.
Oh.
Okay. HA upon MCP. Okay, you will have to write this formula somewhere. We will try to cover some theory to understand where exactly this formula came from. Okay, we are now into middle of this numerical. We will not get into this, but I'll try to explain to you how exactly this formula came. Okay, from where this formula came. So what exactly or how exactly they have used this formula? Basically, they have equated the MCP dt and HA delta T. MCP dt and HA delta T, and by integration they have simplified this formula.
Okay.
See, even you could have done that. Even you could have done that. What exactly you could have done? Like we know that Q lost, like this formula Q is equal to Q convection. So MCP dt is equal to HA delta T ln. Now in this formula, MCP dt is T I minus TE, right?
Yeah.
Ti minus Te, and H, it would be H surface area, and the delta T mean formula would be all these terms, which will look like delta T2. Delta T2 would be Ts minus Te. Delta T1 would be Ts minus Ti, let us say, whole upon ln delta T2. Delta T2 is again Ts minus Te. Delta T1 is Ts minus Ti. You can see this formula, right?
Yeah.
Simply they have rearranged these values and they got this.
Okay.
You should know that when we take log to the other side, it becomes exponential.
Yeah.
You know that, right?
Yeah.
Sure, right?
Yeah, I think so.
Okay.
I can go revise it later. It's fine.
See, okay. No issues. See, in this calculator, while I press this button,
yeah.
they show us ln, right? Ln.
Yeah.
Okay. Ln. But at the same time, when I press shift, and then I press that button, it shows exponential.
Yeah, I know this. Yeah.
Right. Okay. So, so when we take the log on the other side, it becomes anti-log, and anti-log is basically exponential.
Yes.
Yes. So what will happen is, like, when we take this over here, this formula will look like minus HA upon mCp is equal to log to the base E Ts minus Te upon Ts minus Tr.
Okay.
So what they have done is they have simply arranged all these terms and they have got this formula.
Okay.
So it isn't something mysterious. It isn't something that is like came out of the blue. All they have done is they have simplified the formula and they are like, you don't do it, I'm giving it to you.
Okay.
It's like that.
Okay.
They're like, you don't have to take efforts, just use this formula and find the temperature at the end.
Can you do me a favor? Can you look at the exam question in the paper that I gave you, the last two papers, I think?
Yes.
Is it, would I need to rearrange the formula like this, or it's just what they give me I can use?
You don't have to rearrange, just use the formula which they have given, no issues.
Oh, okay.
And it is not something very difficult by the way. Okay, only because you are doing it for the first time, it creates kind of fear. Okay, again you have to do that. It will be like impossible in the exam or something like that, you might think. But believe me, it is something, just do it once or twice and you will be used to of it.
Okay.
Okay, so when to use the formula is the main question, right? Okay, for example, suppose I'm not aware that I have to use the formula. Suppose I'm in a situation, I'm like, okay, I will solve it. It looks like doable. So what I will do is, I know that there is a formula of delta T mean. I know, okay, and I also know the formula of HA delta T. Okay. Okay. I also know the formula Q is equal to HA delta T mean. This Q will be equal to this Q, right?
Yeah.
Okay. What does it mean? It means heat convected is equal to heat either lost or gained. In this case, it is heat lost. So heat transferred will be equal to heat lost by the fluid. So you will be in a situation where when you will equate this two formula, it will look like, okay, 0.09994 into 1008 into 84 minus Te is equal to HA delta T. HA delta T, I don't have the value. Do I have the value of H? Yet I don't have, we'll have to calculate that. Okay.
Yeah.
H, A is surface area of the duct. Surface area would be the perimeter into length, okay?
Yeah.
So it will be like 2 into 0.15. Okay, it's a square duct. So sum of all the sides. So it will be 4 into 0.15, right?
Yeah.
4 into 0.15 will be the perimeter, and simply multiplying it by 10 meter, it will be the surface area.
Correct.
Okay. So this is perimeter and this is length. So that is surface area. And delta T mean, if I substitute, it will look like delta T2 is over here. This is delta T2. Delta T1 is over here. This is delta T1. Okay. Suppose you write delta T2 as TE minus 70, delta T2, delta T1 84 minus 70 whole upon log to the base E, TE minus 70 upon 84 minus 70. Okay, if somebody gives you H, once you know the value of H, in this entire equation, TE will be unknown.
Yeah, and then you can solve for TE.
Looks doable. Looks doable because you believe in your calculator.
Yeah, yeah.
But believe me, your calculator will be like, sorry, I can't do it. And the reason is log in this formula.
Okay.
Whenever a log will have an unknown, your calculator will end up saying, sorry, can't solve.
Okay.
Okay. Only in that case, these people are helping you out. Don't worry that your calculator can't do it. So we will simplify this for you. And the
Mhm.
simplified formula would look like, okay, simplified formula for this would look like e raised to HA upon MCP minus HA upon MCP is equal to TS minus TI upon TS minus TE, right? That's the formula, right?
Yeah.
I hope I've simplified it correct. Okay.
Yeah. So,
Yeah, I've done it correct, I think. Maybe it
Mhm.
should be like TE should be in the numerator.
Mhm.
Yeah, it should be like TS minus TE upon TS minus TI,
Mhm.
outlet upon inlet. So using this formula, because now calculator can solve it. There's nothing wrong in this equation. You have done everything correct, but your calculator can't do it. So you'll have to mathematically simplify it and remove the log term.
Mhm.
Because you were taking it too long, the examiner has helped you out and given you this formula. Simply use this
Okay.
formula and calculate the value of T.
Okay.
Okay, it is just the rearranged way of this formula. Okay, now first of all, we need to have H for this question.
Mhm.
Now the entire effort will be to find the value of H, and only for that they have given us these values.
Okay.
Okay, should we proceed?
Is this the end of the question?
What?
We haven't finished the question, is it?
No, we need to proceed to find the value of H. Should we proceed to find the value of H?
Okay.
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 Okay. The permission was to proceed to find the value of H.
Yeah.
Because we can't find T unless we have the value of H. And to find the
Yeah.
value of H, we need to know if the flow is laminar or turbulent.
Okay.
And to
So
find,
find the Reynolds number.
yeah, if we need to find the value of Reynolds number for this. So Reynolds
Okay.
number Re is rho VD by mu. Rho is
Okay.
being given. They have given us nu. So this can be written as VD by nu.
Okay.
Nu is kinematic viscosity, mu is dynamic viscosity. If kinematic viscosity is given, use this formula. If dynamic viscosity is given, use this formula.
Okay.
Okay. Kinematic viscosity will always have a unit meter square per second.
Okay.
Dynamic viscosity will have unit Newton second per meter square, Pascal second.
Okay.
Okay, you need to remember that. Okay. So first of all, let us find the Reynolds number. Reynolds number, velocity, diameter, and nu. Okay, velocity. I think they have they given us the velocity? No. How to find the velocity? What is the value of discharge volume flow rate formula?
Rho AV.
AV. It's AV.
Okay.
Mass flow rate is rho AV. Okay, that is fine. Just remember that formula. It's okay.
Okay.
We have calculated mass flow rate, right? See.
Yeah.
Okay, let me remove the camera from here. Okay. Okay. See, m dot formula has got rho AV. It means it has got velocity inside. So even using this formula, we can find velocity, right?
Yeah. So we just
All you have to do is just simply divide rho A.
Yeah.
So from here we can find the value of velocity. Velocity will be m dot upon rho A.
Yeah.
Right. So m dot is 0.09994. Rho is 0.9994, and area of cross section is 0.15 into 0.15.
4.44.
4.44 meter per second.
Yeah.
Yeah, correct. Okay. Now substitute the 4.44 and diameter. What would be the diameter? It is not a pipe, it is a duct. Hydraulic diameter. What's the formula of hydraulic diameter? 4A by B. You remember 4A by B?
No, what's 4A by B?
4A by B.
What is that?
Hydraulic diameter, characteristic length.
No.
Okay, just revise the last lecture, okay? In that.
Yeah, it's
Okay,
sorry.
So 4A by P, in that case, area of this would be 0.15 into 0.15.
Yeah.
And perimeter would be 4 into 0.15.
Okay.
Perimeter of square. If you simplify this, you will end up diameter equal to side, okay? So it will be simply like for square, diameter is equal to side itself. So D will be is equal to 0.15 itself. Okay?
Okay.
Substituting this kinematic viscosity, what is the Reynolds number? Just tell me. It is 4.44 into 0.15 divided by 2.097, 10 raised to minus 5. How much?
I got a very big number.
Yeah, it's a big number. 31788.
3 what?
Yeah. 31788.
Why am I always getting this wrong? Give me a second. 2.097 10 to the power 5. Yeah. Can I try it again?
Take your time. Yes.
Yeah, 31759.
Yeah, fine, correct.
Okay.
So this is the value of Reynolds number, which is more than 4,000.
No, less than. So it's not turbulent.
It is more than 4,000, right?
Oh, sorry. I read it's 3,000. Yes, it's more.
So what? How's the flow?
Turbulent.
Turbulent, right? So the flow is turbulent. Confirm, right?
Yeah. Yeah, confirm.
The flow is turbulent. So we need to use the Nusselt numbers equation for turbulent flow in the duct.
Okay.
Okay. I will just get the page out for you where they have given you the formulas, like the page of formula sheet. This formula sheet. So formula sheet has Nusselt numbers equation 0.023 RE raised to 0.8 PR raised to N, right?
Give me a second. I'm just pulling up.
Nusselt numbers equation is 0.023 RE raised to 0.8 and PR raised to N.
Yes.
Right? This is for turbulent flow, isn't it?
Yes, correct.
So now, is the air getting heated or is the air getting cooled?
The air is getting cooled.
Cooled. So the value would be 0.3.
Yes.
Okay, that's how you end up making the decision of using Nusselt numbers equation. Okay. And this equation will be equal to H D by K. Right?
Yeah.
Okay. See, the K formula has been given to you. Diameter or the characteristic length is 0.15. If you can calculate the value of Nusselt number, you can easily calculate the value of.
Why does it equal to HDK? HDK. Why does it equal to HDK?
Nusselt numbers equation, HD by K or HL by K.
Oh, you find it and then you replace it back. Okay, yes, correct.
You remember this formula? Nusselt number.
Yes. It's just that I learned it, like solved that, then later put it back in.
No. You should always solve one question, but solve it in an extent that you know everything in and out. Don't try to understand the solutions. Okay, that is the worst way to understand the subject. Never read the solution. Try to make the solution yourself.
Okay.
See, now all we have to do is simply find the formula, value of Nusselt number. We have the RE.
Yeah.
We can substitute RE over here. We have the Prandtl
Yeah.
number. We can substitute over here. So we can find the value of Nusselt number, right?
Yeah.
Now use the calculator and tell me Nusselt number. Zero 0.023, RE raised to 0.8, PR raised to 0.3.
83.1578.
Correct. 83.1578. Now you can equate this to this HD by K, out of which D is 0.15 and K is this.
Yeah.
0.02953. And tell me the value of H.
Okay.
That's the answer.
D is 0.15, right?
Yes.
It's 16.37.
H is 16.37.
37.
And you got the value. Watt per meter square Kelvin. Now you have the value of H. This H can be substituted over here. Area is surface area, which is perimeter into length, right?
Yeah.
Perimeter into length is equal to 0.15 into 4. 4 into 0.15 into length 10 meter. Why? Because it is surface area.
Area, yeah.
Surface area. So H is something that you have already calculated. Area is something that you can calculate now. M is already being calculated, which is equal to this 0.09994. Cp of air is 1008. That's how you can calculate the LHS. Once you have the LHS, T surface is 70, T initial is 85, and the only unknown would be T. And the answer and the question would be done.
Okay.
Do it. Calculate the LHS. Calculate the LHS. Just calculate the LHS part. Substitute everything in what is.
I got 0.974.
LHS? Okay. E raised to minus.
I haven't finished that yet. Give me a second.
16.7. Surface area is 4 into 0.
I got 2.6511.
How much?
2.6511.
Is 0.09994 and it is 10008. 0.377.
Isn't that just the power portion?
E raised to something.
Okay, I try it again.
See, I have substituted E raised to all.
Okay. Yeah.
Okay, don't simply calculate the power. Calculate it with the E raised to something. Or if you have calculated the power, you can.
Yeah. Is it negative HA?
No. Even if I have taken negative, yeah, negative HA, correct.
Okay.
We can do one thing. We can also continue with numericals tomorrow in the morning.
Ah, yes. I'm very tired already.
Yeah.
Yes, I got.
How much? 0.377?
Yes.
Perfect. Okay. Do you know how to take the alpha x and all unknown in the calculator?
Alpha?
Okay. Like,
No.
can you solve it for unknowns in the calculator?
No, I've not done that before.
Okay. That is something which is very convenient, by the way.
Oh, okay.
Okay. Maybe I will just go through your calculator, how it looks. Just take a snap and send me, okay? If at all I can,
Okay.
I will try to help you out how to use a calculator also, because it looks magical. You know, like, see, what I will do is I will write the entire equation. Okay, like the answer minus and 70 minus unknown. So it will, I will write alpha x upon 70 minus 85. See how my equation looks. Just look at the equation in my calculator. Could you write the equation in this form?
I can't see it clearly. Oh, no, I can't. I've not done that before.
Okay. See, once I write this, I will just simply press shift solve equal to 0, and it will directly give me the value of x, that is 75.
Oh, okay.
And answer is same. 75.6 is the answer.
How did you do that?
These are small tricks you must know about your calculator.
Okay.
You just take a photo of your calculator, okay? I will help you
Okay.
with the calculator also if possible.
Okay.
Okay. I think we should stop now. Just go through everything.
Yeah.
Try to solve, if at all it is possible for you, at least one question today. At least one.
I'll look through this 7 and I'll do it tonight.
Even that
And
is
then I'll
fine.
send you.
Even that is fine if you just go through the questions which I have solved. Okay.
Okay, Ken.
If that is not the case, try to pick one question and don't look at the solution. Make mistakes, whatever you want, and see if at all you can do or not.
Okay, Ken.
And let me know how is it, like what's the status, so I will try to help you accordingly.
Okay. Okay, Ken. Thank you.
Let's stop. See ya. Have a nice day. See you tomorrow morning.
Thank you. Bye-bye.
Bye-bye.